the workshop this morning. So to begin, we'll have Yang-Hui He speaking from the London Institute, affiliated as well as University of London, Oxford, and Nankai. And he'll be telling us this morning about how we can think of universes as big data. So please go ahead whenever you're ready.
Thank you so much for having me at this conference. And it's a shame I can't be there in Trento. I've never been there. I wish I could go there sometime in the near future. My understanding is that the audience is fairly mixed, so I would try to give a little bit of the background of why this kind of ideas show up in the kind of thing, the stuff that we do. So I mean, it's clear that that algebraic and differential geometry and topology and representation theory in any combination of these words is the right language for physics. You know, you can think about gravity in terms of, you know, Ricci 2 form of tangent bundles. You can think of elementary particles, irreducible representations of a Lorentz group, and so on and so forth. So, you know, much of the 20th century has been this dialogue in translating problems in fundamental physics to mathematics in this flavor. Of course, in the 21st century, this is a very exciting era, because into this language between this dialogue between pure mathematics and fundamental physics is added computational mathematics and computer science. This is a natural way to go, and I'm going to mention why fundamental physics, especially in string theory, has produced so much data that's right for mining, if you wish. So let me just give one slide reminder of the basic setup of string theory. I won't talk much more about this. It's just that, you know, we have this 10-dimensional theory of quantum gravity, and we need to reduce this to our world of observables, you know, of the standard model and of the of GR. And so we need to somehow address this problem of the six missing dimensions. These dimensions could be either small, which is kind of compactification, which is the case I'm going to mainly talk about in this here, and there could be large, in which case you can talk about ADS-CFT. I think Koji yesterday gave this beautiful talk about the ADS-CFT correspondence in this current context of machine learning. So in this compactification scenario, I mean, this story is really, really old. It goes back to 1984, when essentially the first string revolution realized this equation, that this is probably the indisputable equation in string theory. All right, this is clearly true. And the point is that these guys realized that the discovery of the E8 cross E8 heterotic string, which came naturally from a lattice structure, momentum lattice structure, that this E8 is very good because it embeds the standard model through just pure group theory. And these extra 6 dimensions can be further complexified into a complex 3-dimensional manifold, which at the time, so they knew that this manifold is Ricci flat because it satisfies vacuum Einstein equations, and then it also has to satisfy SUSY constraints, supersymmetry constraints, which made this manifold Kähler. So Ricci flat, of course, physicists were familiar with this since Einstein, but Kähler was something that's slightly new. They didn't even know that this condition is called Kähler. So Kählerness here simply means it's a complex manifold whose potential, whose metric comes from a double derivative of a single scalar potential. So that's where things were in 1984. It is very interesting that the pure mathematicians were thinking independently of exactly the same problem. So it's kind of, whenever you have this convergence, you know, your nose tells you this is probably the right thing to do. So let me just give you a brief reminder why mathematicians were thinking about this. So this story, of course, goes back to Euler and Gauss and Riemann, right? You know, the Riemann uniformization theorem in complex dimension 1 or real dimension 2 is essentially this beautiful story of the relation between topology and metric geometry, right? So here there's a trichotomy classification of possible orientable surfaces. That the topology goes this way is due to Euler, but then Riemann and Gauss realized, well, the actual metric divides into three families: positive curvature, where genus 0, where genus is 0, zero curvature, where genus is 1, and what we call surfaces of general type, which, or complex curve of real surfaces or real orientable surfaces or complex curves of general type, which is of negative curvature. So this torus, which is Ricci flat, is sort of right at the boundary between positive and negative curvature. So that's this summary here. And then so over the years, all the greatest mathematicians in geometry and topology have been trying to relate the story. As you go from left to right in this equation, you're going from topology to intersection theory to differential geometry to index theory and algebraic geometry. So that's a great story for complex dimension 1. However, if you go up in dimension, high dimensional manifolds are very, very difficult to tame. But nevertheless, for the Kähler manifolds, there was the conjecture of Calabi in the 1950s. So you see this almost 200 years since Euler in trying to generalize this story. And I won't bore you with the details, but the Calabi conjecture essentially is a statement about how the Chern class controls, how algebraic geometry controls the topology and the metric geometry of these manifolds in arbitrary dimension. Of course, not for any manifolds, but for Kähler complex manifolds. So Yao proved this in 78, for which he was immediately awarded the Fields Medal. So you can see why the mathematicians were interested in this problem. So because it has such an ancient history, and it goes into so many different branches of problem. So it just so happens that the Strominger was Yao's postdoc at the IAS in 1985, shortly after their paper. Right? So it's kind of really fortuitous. The Strominger can just go to Yao and ask, what are these Ricci flat Kähler manifolds? In fact, what is a Kähler manifold? And then Yao, being the world expert on the subject, told him everything. And then physicists and algebraic geometrists started talking, and that's been a really wonderful dialogue since the 1980s, which continues still today. And this is why algebraic geometrists like string theory, because of this story, because it keeps on giving, string theorists keep on giving algebraic geometrists new problems to work on, and like crazy conjectures, which is sort of orthogonal to the approach they normally think about these things. In any event, the word Calabi-Yau came from this CHSW paper of Candelas, Horst, and Strominger and Witten. And so it's actually the physicists who called it Calabi-Yau. Instead of, Ricci flat Kähler complex manifold is a bit, mouthful. So they call this Calabi-Yau in honor of the Calabi conjecture and Yau's proof of this. So, so let me just give one slide on how to actually construct this. I told you about the torus, and we know that's a Calabi-Yau of dimension 1. So the constructing manifolds in geometry is not a trivial thing, right? You can go very quickly into the differential language. You can start patching, patches and use, gluing properties. But one of the favorite ways that geometers like to construct manifolds is to use the language of algebraic varieties. I mean, this is actually much simpler in some sense than differential geometry, because an algebraic variety, all it is just the vanishing loci of polynomials, right? So, or systems of polynomials. I mean, we know, for example, x squared plus y squared equal to 1 is a circle, right? And that is indeed what we call a one-dimensional real algebraic variety. So in complex dimension 1, a torus can be realized as a cubic in complex projective 2. So this is the famous cubic elliptic curve. So number theorists love this sort of business. And then you can just go up in dimension, right? So in complex dimension 2, you can realize the next Calabi-Yau, which is a quartic in CP3. There are other constructions, but this is one of the standard ones. So, but you go up in dimension, you enlarge your embedding space, which is always some complex version of projective space. We don't embed it in Cn because we want the things to be compact. So you add a point in infinity to make it Cpn. So immediately Calabi-Yau threefolds, which is what we're after, right? After all, we want the three-dimensional version of the story. Yau immediately provided the physicists with 5 manifolds. You can take the degree 5 polynomial. This is the homogeneous degree 5 polynomial in 5 projective coordinates of CP4. And this is known as the quintic manifold, Calabi-Yau manifold. And there are a couple of other ones. You can see these are, intersections of a cubic polynomial, another cubic polynomial, so on and so forth. So the landscape, if you wish, of Calabi-Yau threefolds went to 5. immediately, because there are these instructions that give you this very explicit. You take this complex polynomials, and the locus cut out by these complex polynomials are clavia. Fine. And then what's more beautiful about this paper is that, as I said, the idea is to translate physics into the language of geometry. So this paper did, in addition to this, translated the particle spectrum. So this is something that's relevant to physicists, and in particular to this community, to the audience. In E6 gut theory, I mean, of course, now we can. This is just a brief. This was preliminary constructions gave E6 theories, because it's here. We're now much more sophisticated. We can go straight to the supersymmetric version of the standard model. But just very briefly, the 27 bar representation of E6 are naturally represented into the generalization of the Betti numbers for these Fabio manifolds, and they're called Hodge numbers, the H21 and H11. The details are not important. The idea is that this is a very, very unusual thing, in that generations of fundamental particles of quarks and electrons correspond exactly to topological quantities of manifolds. I think, to my knowledge, this is the first time something like this has been written down. This is back in 1980, so it's kind of nice. But now this is becoming very, very standard to interpret fundamental particles in terms of cohomology theory or topology in algebraic geometry. So in particular, of course, we know there's 3 generations of particles, but from the generalized Euler theorem, that this difference of the Hodge numbers is half of the Euler number. So in addition, the physicists asked Yao, not only are they, give me some Clavier threefolds, but also give me Clavier threefolds which have Euler number plus minus 6. And these obvious 5 just didn't work, right? So this launched, in some sense, the beginning of data science in theoretical physics, and certainly in algebraic geometry, because algebraic geometrists won't, they'll tell you a couple of examples and whether it exists or not. Yao's proof of the Calabi conjecture is a famous example of an existence and non-constructive proof. He showed that there exists this Ricci flat metric, and even till today, not a single analytic expression for a compact Clavier metric has ever been written down, because it's just too complicated. So it's a beautiful existence theorem. So it also gives you a flavor, right? Algebraic geometrists don't go, they don't get a piece of paper or get a computer and start writing things down until, I would say, in the last 5 years or so. So to address this question that, these immediate examples that Yao provided didn't give these topological constraints, which would then give the correct particle physics. Candelas and friends took on this journey of 5 years to try to generalize this, right? So instead of construct, a single projective space, let's try to do multiple projective spaces and so on. Again, the details are not important. I'll just give you a flavor of the kind of thing. So, you can represent these manifolds as matrices, encoding degrees of these polynomials in some products of projective space. The thing I want to emphasize that any algebraic variety can be condensed into some kind of information like this. So just bear that in mind. So algebraic geometry is extremely amenable to good data representation because by definition it is about intersection theory of polynomials. So they had to recruit the best supercomputer at the time, which was the CERN supercomputer in the 1980s, and they were able to find about 8,000 new manifolds. These manifolds, mind you, are completely new to the math community, because, maybe except for a few cases, because, mathematicians don't go on computers and start writing examples, right? That's not what they do. And similarly, there are other ones, there are other databases, what about putting weights on these projective spaces and so on and so forth. The most remarkable one is this one done by Krotz and Shkarka over a course of 10 years, which is to construct his manifolds out of what's known as reflexive polytopes. And again, this I won't bore you with the details of torque geometry, but there is a so this is basically a reflexive polytope. It's just something that has it's a lattice polytope with a single interior point, such that all of the bounding facets is distance 1 from it. So toric geometry is a subfield of algebraic geometry, which turns algebraic geometry into combinatorics. So there's a very nice theorem of Battir and Borisov says that you can construct certain Clavier manifolds using pure combinatorics of lattice polytopes. So what's interesting is that, there are 16 of these things in dimension 1, which is known to the Italian school of geometry in the 1800s. But it had to wait 100 years to answer what's the one in next dimension, right? And then it's Kreutzer-Schacke really answered that question, which is the complex dimension 2 case. But what about the complex dimension 3 case? And that took this impressive number in 2000. And they came up with this many reflexive polytopes, and therefore at least this many Clavier manifolds. And the next number is incidentally unknown. There's the combinatorics is so simple you can explain to a high school student, and yet there's no theory to even try to predict what the next number is. So it's kind of interesting. In any event, this landscape of Clavier manifolds grew from like handful to 500 million, right? Which is respectable for even by today's standards for big data, if you wish. So I love Flash in this. I think I've used this multiple conferences, but I love this quote. And basically, this of course, the age of data science in physics has been very, very old, right? CERN's been used in machine learning for decades. But in terms of the string and theoretical high energy community, it's relatively new. But of course, it's not really, because even back in the 80s, people were data mining this kind of stuff and trying to see what patterns you can spot from this. So if you want to read more about it, here's a shameless self-advertisement. You can read more about sort of the history and some of the constructions of this Clavier landscape from this book which just came out last month. So the point is, I'm just now giving you a flavor. Oh, before I get to this, so this is nice. So this is just Clavier manifolds answering an old question. So there are these compact, smooth Clavier manifolds on which you can put string theory, which then creates universes, right? And each manifold gives a potential universe of a different property. And we would like, in principle, sift through them to see, which of these have properties that are akin to our universe, like 3 generations of fermions and that kind of stuff, like a pair of Higgs. So just to assure you that we're not just, homing in on a null set of random search, some brute force, small scale brute force searches have been going on since the mid 2000s. And you can actually find the exact minimally supersymmetric standard model. So I have to put minimally supersymmetric because this entire construction always relies on supersymmetry. You can take different flavors about supersymmetry, but at least that's the context I'm going to work with, just to be very concrete about at least what the geometry dictates that gives us. So whether or not this space of Claviers, there is a selection principle in this space of Claviers towards the right geometry is still an open problem, and it's still the biggest problem in this whole business. Is that fine? You've given me this 500 million or whatever, growing. It's still growing. That's just 3 classes of constructions I've given you. But can you give me some kind of a selection principle that gives universes like ours? That's 1. And 2, how much can you exhaustively search through this to give properties of universes? So when I say properties of universes, I mean a universe with something that's like a standard model, and something that has the GR, and something that has the right behavior of physics in the low energy. But this, so what I've just given you a flavor is the landscape of Clavier compactifications. But since '95, there's been this massive explosion in string dualities by all of these people. And what that led to is not an amelioration of the situation, but a far more intimidating situation of, well, in addition to compact Clavier manifolds, you have to now consider G2 and all of the non-compact manifolds, and what about Clavier fourfolds, and what about adding fluxes? So that's when numbers like 10 to the 500 are beginning to drift into the public conscious. So I want to emphasize, so this is called vacuum degeneracy problem string theory. There's just this proliferation of possible solutions. And this proliferation is partly due to the fact that, so if you forget about the physics for a second, the number of topologies of manifolds as you go up in dimension grows exponentially. So that's the basic problem. So we know in dimension one, you have Euler's classification theorem, but then you go up in dimension, it just goes wild. So that's partly the reason why this is, combinatorial problems also grow exponentially as you go up in dimension. So in some sense, string theory trades a very difficult problem of quantization of gravity by another very, very difficult problem, which is how do you find the right compactification? How do you give the right selection principle, if you wish? So just to summarize where we are, so the good thing is that, physicists have bitten the bullet and have been compiling this data, and it's all freely available, and people should know. I've given some links, you can check later. And the good thing is, so you can sift through this data and play with it. I highly encourage anybody who can't with insomnia, just download them in the middle of night and just try to play with it. They're all freely available. So here's some links, and they are typically on the order of a couple of gigabytes. So if you want to say, like, I want to know the space of Calabi-Yau manifolds, I want to know the space of toric varieties of certain type, they're all, you can download them and play. That's the good thing. And this is a really combined effort, about 20 years, 2 decades, between physicists and computer scientists and pure mathematicians. And it's really quite remarkable. The bad thing is that if you want to just take this gigabytes of data and just even sifting through and computing the topology, the metric geometry in order to sift through the right physics, it's exponentially hard. I mean, in a technical sense, if you want to dig into any of the details of the computation, you're going to run into exponential problems. There's a famous thing in algebraic geometry, in computational algebraic geometry. The first thing you do is to put it into Grosvenor basis. So the Grosvenor basis is a generalization of Gaussian elimination for polynomial systems. Gaussian elimination is n log n in number of variables. So Grosvenor basis is famously double exponential in number of variables. So this is just not practical. So so it's natural to ask yourself the question, well, you got all this big data. I mean, it's natural to just try to machine learn it in some kind of, it's a not natural way. So, and that's something that I was asking back in 2017, which is, interestingly, several of my friends independently were thinking about similar ideas of applying machine learning techniques to whatever your favorite problem is in string theory. So these guys were thinking about finding volumes. Fabi was thinking about problems in finding bundle cohomology, and these guys were thinking about how to find specialties in the toric landscape. So what I was thinking, well, as I emphasized in the beginning, any algebraic variety, and so effectively any manifold, can be represented in terms of some kind of tensor input. Right. So for example, the CC, I'm going to give a very specific example in a minute just to make it concrete. And what algebraic geometry does in some sense is to take that input and try to compute an integer out of it. Right. The integer is some kind of a topological invariant or something like this. So this is a typical problem. Of course, there are other problems like can you numerically compute metrics, and that's something I'll get into as well. But a large part of what algebraic geometry is, phrased in the language of data science, is this flowchart. And so that's kind of interesting, that you can do this sort of thing. Just to give you a flavor, so you can see this kind of progression in where the field is going in some sense. So these are major annual conference series, right? So the first strings came in 1986, so it's been happening every year since 86. And why? That's precisely because it came right after the revolution that I talked about. This first, the heterotic string, the first string duality came about from there. And then the first string pheno came in 2002, partly because of, I think, because Kreuz and Schak and these people started providing all this data that you can start sifting through, and so on and so forth. And 2017 became the first string data conference where big data techniques such as machine learning are being introduced to, it's becoming part of the standard tool of what we call the string community. So this is nice that there's an enlarged dialogue with expertise from different directions. So of course, this is this audience is very much versed in machine learning. I'm very much an expert, a non-expert, and very much of a novice in this. But I just want to flash you this diagram, which machine learners love, which is the NIST database, the NIST handwritten digit recognition problem. The reason I phrased this, a lot of the prototypical problem in machine learning is the supervised learning problem of recognizing this image to be the number 3, where this image is given by 28 by 28 pixels by RGB data. So this is we know this very well from an ML community. So now let me go back to algebraic geometry. So of course, your neural network, unless you seriously try to build in activation functions which know about the algebraic geometry, and that has been done, and I will mention that a little bit later. It doesn't really care about what your input, what this picture is, right? So let me just give now a very concrete problem. So let's take an algebraic variety. This is in fact what we call a complete intersection Calabi-Yau manifold in dimension 3, which is actually one of the compactification manifolds. So the way to read it is that it's the complete intersection of 8 hypersurfaces of multi-degree given by this in P1 cross P1 cross P1. So they're products of projective space as an ambient space. You think about this direct product of ambient space, which is of this whatever this 12-dimensional space. 11-dimensional space, and then you slice them out by polynomials of these multi-degrees. So you just literally write homogeneous polynomials in this projective coordinates to this various degree. And then, so that's your manifold. You literally, I mean, of course, this is too big a dimension, but you can plot this in Mathematica if you wish, and you can see, the loci of this actually give you a manifold which looks like a Calabi-Yau. Of course, this is a 6-dimensional real manifold, and the only way to visualize is you take slices, and you can do that. So let's do a typical computation of what you do with this information. The algebraic geometry tells us to compute, give you some configuration like this, and I can compute, say, its Hodge number. So this Hodge number is a complexified Betti number, and this number essentially counts the number of holes in dimension 2 for this manifold. Right. So who cares? What about this cost? And because of this translation, this dictionary, this number of holes actually corresponds to the number of 27 generations of particles in E6, for example. So I mean, this is a toy example. We can get more sophisticated. If you want to ask for SU3 cross SU2 cross U1, then you also compute what's called equivariant cohomology of certain bundles on these manifolds. I won't bore you with the details. But there is a way to do it. And it's, as I said, in algebraic geometry, in computational algebraic geometry, there's this doubly exponentially expensive way to do it. And the way to do so, this is kind of stuff that I've been doing, since my graduate student days. And that's the available thing you do. And you chase long exact sequences until you cry, basically. And you get some kind of answer. But luckily, for huge classes of these manifolds, there's this wonderful book of Hooch, and who was in collaboration with Candelas and friends. They actually computed the cohomology for these many manifolds. So in particular, the H11 for the 8,000 or so sissies, and the H11 and H21 for the 500 million toric variety Calabi-Yaus have all been computed and compiled into databases. So that's kind of nice that this is doable. So. Whoops, sorry, that was the wrong button. So I mean, you see what's naturally what one naturally needs to do, right? You treat this as if it's some kind of pixelated image, and you supervise train on this association exactly the same way as you would do with this. So what is surprising, of course, is that this problem had variation. People write numbers smallly and then differently, and then there is also perturbation. People, a little bit perturbation here and there. It still remains a 3. When I started playing with the algebraic geometry data set, I never imagined in a million years, especially since I was such a novice to machine learning, that this could even possibly work. Because you deform this as a different manifold, right? That there's no reason why a generic neural network could even classify this problem at all, right? It could learn it, and I was very surprised to find. So I did some initial experiments, and then with my students and my student Kieran and my collaborators, it actually works to surprising accuracy. So I should emphasize this kind of idea. So more recently, just in the last year, Urban Finatello, they used a much more sophisticated neural network in image processing, and they were able to get accuracies up to 99.96% in actually doing this computation in a matter of seconds, right? Instead of going through this double exponential algorithm to compute them. So somehow there is structure in algebraic geometry that's you wouldn't have imagined to work for image processing kind of neural network. And this is still mysterious to me. So I will mention a little bit more about this on later. And then you would do other kind of problems in algebraic geometry. Right? Can you distinguish elliptic fibrations? You can see from the learning curve. So this is just accuracy to percentage data, percentage training data. Once you hit 30% training, okay, small training is a bit of a problem, but once you hit like 30% training, you essentially at 100% accuracy in distinguishing really hard problems in algebraic geometry. So there's something that's very much amenable in the very structure of algebraic geometry, at least, which luckily is the most useful thing for string theory, that is I still must confess, mysteriously amenable to this kind of machine learning paradigm. So since then, there've been so much work on this, and so I can't possibly give all citations, but there's some interesting ones, like you can also do numerical Clavier metric, and I think I must be missing loads of. So there's more recent works of Jejala and Mishra and Anderson and on Clavier metrics in addition to this. So that's kind of interesting, and of course I can't resist but to mention 2 other friends on this conference who are going one step deeper to even actually trying to interpret quantum field theory itself as some kind of machine learning algorithm. And that's actually not what I'm doing here, right? I'm taking a structure in mathematics, which is obviously useful for physics computation, and I'm trying to see why, or I'm in the process of trying to see why is it that one can understand such computations. So that leads me to the last part of my talk, which is, well, that's actually kind of interesting, that algebraic geometry is so amenable to a generic machine learning algorithm. One might argue is that because essentially all of computational algebraic geometry is about finding kernels and co-kernels of matrices. So every single step in every single part of algebraic geometry at some level boils down to this computation. It seems like a very fancy field, but the nitty-gritty details of that is about finding kernels and co-kernels of matrices. And that might be something for which neural networks are very good at, and this needs to be explored further. So but what about other branches of mathematics that are obviously also useful to physics? So that got me thinking. Of course, mathematicians have been thinking about this kind of stuff all the time. People like Kevin Buzzard and Harold Davenport. They write this what's known as the automated theorem proving program. Then this is a program that goes back to the 1960s. Can you use AI to try to prove theorems. Right? But this is what when I'm talking about is sort of a parallel to that program. You know, we're not writing sentences, logical sentences in mathematics. I just have to ask a much simpler question. If I give you, you know, say, I don't know, 100,000 cases of this data, I'm not going to tell you which branch of mathematics comes from, or sometimes it's labeled, and I'm not going to tell you what this labeling is either. The question is there a pattern, and can one conjecture and then prove a possible formula about such pattern? And two, which branch of mathematics do you think this data actually comes from? Does it come from group theory, or does it come from geometry or differential topology? So that got me exploring with various collaborators. So one of the first things we did was with Min-Young Kim, which is to look at Cayley tables of finite groups. Now, this is obviously another thing that's of great interest both to theoretical physicists and to pure mathematicians. So, you know, the Cayley table is just a multiplication table. For a finite group, this is just the finite matrix, and it's a finite matrix, which is in fact a Sudoku, a Latin square. And so it's a 1 to n, but no repeats because you have to obey some group multiplication law. But not every Sudoku is a multiplication table of a finite group. So of course the GAP database of finite groups has 3.5 million groups. Of course, we didn't take all of them. We took, you know, I don't know, something like the first 1,000 or so, and then establish a database of Cayley tables versus non-Cayley tables. And the support vector machine was able to find, you know, to this kind of accuracy, that something is a proper group. That's kind of interesting. What is more surprising is the following problem. One of the deepest problems in representation theory is the theory of simple groups. So if you take a finite group, the simple group is this very special class, which essentially, you know, by semi-direct products, you can create the other, you know, all groups. But it seems very difficult to isolate the space of simple groups. And yet, if you plotted this, if you just flattened the Cayley tables of simple groups versus non-simple groups, a support vector machine was actually, you know, it was able to find a hypersurface which kind of order by order. I mean, the hypersurface changes, of course, because, you know, the space of finite groups is infinite, but it was able to differentiate them to, you know, something like over 96% validation accuracy. This is very surprising. This tends to suggest, so this is of a proto-conjecture. This is what I mean by conjecturizing. This is a very strange way of doing group theory. We should sit down and try to see why is it there exists this separating hypersurface. So to my knowledge, this is the first time that machine learning has been applied to a problem in representation theory. And
hey, Yang-Hui,
yeah.
just you have a bit less than 5 minutes left.
Okay, no problem. Yeah.
Thanks.
So you can try with other problems in, say, in combinatorics, right? And then, you know, and graph theory, and you also have, you know, different types of behavior. And of course, you know, it goes back to this problem. Something's got to go wrong. Certainly, there must be branches of mathematics which are completely amenable to machine learning. And you expect that the distribution of primes is exactly one such a problem. So I won't bore you with the details. And it seems to initial experiments in prime prediction or the prime characteristic prediction is indeed as bad as you would expect to be. It's almost completely random. Nevertheless, the field was surprisingly is when I started working with here with my students on some kind of some problems in arithmetic geometry, but here I was working with like card-carrying algebraic geometers, and we were finding that for problems in arithmetic geometry, whenever you phrase your problem from in number theory to arithmetic, arithmetic geometry to algebraic geometry, the problem suddenly becomes much more amenable to your generic problem. So we're using things like Bayes classifiers and decision trees, and they were able to tell very intricate structures of elliptic curves. This suggests, why, if you think about Fermat's last theorem, it's hard to prove if you just use analytic number theory. But Wiles was able to prove Fermat by rephrasing, or not Wiles, but this whole this whole history was to rephrase that problem into arithmetic geometry, into algebraic geometry, and then the problem became crackable. So somehow this is in line with this in this problem. So let me just summarize. So this kind of ideas of using machine learning is certainly extremely useful for the string theory landscape for physicists, right? So you can try to classify and categorize landscape data in terms of vacuum selection. You can also try to predict and estimate results whenever you're beyond computational power. And in mathematics, I almost want to establish certain hierarchies of problems to see whether our intuition of where the difficulty of problems in mathematics is sort of more or less in line with not the complexity of the problem, but with how much machine learning algorithms struggle in terms of where this data actually comes from. And so, yeah, I think, so I mean, of course, there's an increasing number of ideas of using machine learning to understand the structures of mathematics and fundamental physics. And several that have appeared just in the last 2 years are here. So I think there's a lot of promise in this direction in fundamental theoretical physics, for sure. So thank you very much.
Okay. For that very nice talk. So we have some time for questions. Does anyone have a question they'd like to ask either online? Oh, I see Biagio. Would you like to come up front just so we can see you?
Hi, Yang-Hui. Thanks for a very nice talk. I can see that you are using methods of deep learning which are local. Have you tried with topological data analysis methods that are supposed to capture the topology better?
Yeah, that's a very, very good question. So the only one that I've tried on is actually with prime numbers, because I'm kind of obsessed with it, because I couldn't use deep learning techniques or any of the standard classification techniques to try to crack the prime curve. So let me just give you 1 second of what I was trying to do here is you label you just get a row of integers, and you label one is it's prime 0 if it's not prime, and you slide a window, say length 1,000, and you want to predict the next one outside of this window.
Mm-hmm.
So deep learning techniques are completely useless to this problem, because the primes are really quite randomly distributed. And what's even worse, sorry, not just whether it's prime or not, but whether the integer has even or odd number of prime factors. So then I tried to put these vectors, these input feature vectors, into TDA to see whether I could get feature extraction from there. And so far, I haven't had any luck either. Okay. I know people in TDA community have been doing this for I can't remember. I think Chirafeli, maybe, I can't remember the name, on the Kreuzerschacke data set, and he's done some nice barcodes for this kind of distributions of data, of the KVL data. And but what can one say about it? I'm not so sure yet, but there's certainly something to be tried.
Okay, thank you very much. Thanks a lot.
Okay, do we have any other questions, either online or in person? So maybe while people are thinking, I'll ask a question of my own. So I was curious where you think linear algebra would fall into, or which side of the fence it would fall into in terms of machine learning. I mean, in particular, in lattice calculations, often what we are bottlenecked on is inverting repeatedly these Dirac matrices, which are large, but fairly sparse matrices with some structure to them. Do you think that would be amenable or not amenable to these sorts of machine learning type approaches?
That's a very good question. I think that my gut feeling, even though I have never tried, but that's certainly something to try, is somewhere that I think that problem smells closest to graph theory, possibly because we're talking about sparse matrices. And that is actually not too bad, unless you want to do things like deciding Hamilton-Euler cycle kind of problems. So maybe you can set something up. So what do you want to do exactly? If you want to, I'll give you, like, I throw in a bunch of matrices, and you want to would numerically find, say, one entry of the inverse of such big matrices or something like that?
Yeah, so typically it's finding a few columns, say, of the inverse. And the matrices do take this sparse form. As you said, it's sort of like a stencil or a graph on the lattice is what the matrix is defined as, but with some data input. So, the actual values in that, in this sort of circulant form are given by the lattice configuration that you're currently trying to invert for. So you'd like to do this repeatedly, but with different data, similar structure every time.
Right. Right.
But yeah, it's interesting that the graphical, I guess these graphical properties are amenable. So maybe that does suggest there's.
Yeah, but not some of them are more amenable than others. I really want to uniformize all of the data. So what I really should do is to take all of my data to be binary inputs, and say even the binary classifiers is completely uniformized, and then I take through different fields and just start listing them. Like so this is sort of a meta-analysis. This is meta machine learning in some sense, right? I want to see how machine learning does well to different data. There was a bit surprising here that the Hamilton cycle versus Euler cycle are about the same level of accuracy. So one of them is actually NP-hard, and one of them is like polynomial. So Euler cycle is one that goes through every edge once. The Hamilton cycle is that goes through every vertex once. So the Hamilton one is the traveling salesman problem. And the Euler cycle one was solved by, I think, Euler's student, and there was a polynomial time to check that. But they gave, well, at least stochastically, the same kind of a behavior. So, which is encouraging in some sense, because just because Hamilton is NP-hard, it doesn't mean that you can probabilistically get like 99% of the time correct. And there are really sophisticated algorithms out there to sort of stochastically solve this kind of problem. So I would definitely try. That was a wonderful suggestion, because I don't know anything about Lattice, but it would be really interesting. Just detach from Lattice completely. Just give it, I don't know, 100,000 matrices of a fixed size, and you want to predict the particular entry in the inverse, and see how well you get. That'd be like totally cool to try.
Right. There's a pure linear algebra question that one could ask here.
Yes. Absolutely.
All right. Well, thank you.
Absolutely.
Okay, so we maybe have time for one more quick question if anybody has one on their minds. But I'm not seeing anything either in person or online. So I guess please join me in thanking Yang-Hui again.
Thank you very much for having me.